you should have a study plan and have some structure around how much time are you going to spend on a daily basis or a weekly basis towards completing this course. Then you can also sign up for an Oracle Cloud free tier account to get some hands-on experience, though it is not mandatory and it's not necessary to have hands-on experience, particularly for the exam, but it's always a good idea to get some hands-on experience to understand and see how these services really work in action. As you are going through the course, you should take ample notes. We also have transcripts available in 29 languages, so you can download those transcripts and make use of them. But you can also take notes, complete all the skill checks as part of that module, and then finally review exam prep lesson and take the practice exam before you take the final certification exam. At any point in time, if you have a specific question about the course material or need extra help, fill out our Ask Your Instructor form, and our expert instructors will get back to you within a few hours. We also want you to get the most out of your learning experience, which is why we have created this community space where you can connect with other learners and subject matter experts. If you have any questions or want to start a discussion on a particular topic, this is the place to do it. Please also provide us feedback. This is the only way for us to figure out what is working, what is not working. So give us ample feedback. And also you can rate the course all the way from 1 to 5. And we look at these ratings and then we do course correction from time to time. And that's it. Keep up the excellent work. I will see you at the next milestone in your AI journey. Good luck and thank you.
Hi, and welcome to this module on AI Foundations. My name is Nick, and I'm a senior cloud engineer here at Oracle, and I'm so grateful that you're here. Now, before we dive in, let's take a look at some of the objectives of this module. By the end of the module, you'll be able to explain AI concepts, describe common AI domains and tasks, and distinguish between artificial intelligence, machine learning, and deep learning. Now, let's dive in. So what is artificial intelligence? Well, the ability of machines to imitate the cognitive abilities and problem-solving capabilities of human intelligence can be classified as artificial intelligence, or AI. So what capabilities or abilities are we referring to? Well, let's take a look. Human intelligence is the intellectual capability of humans that allow us to learn new skills through observation and mental digestion, to think through and understand abstract concepts and apply reasoning, to communicate using a language and understand the nonverbal cues such as facial recognition, tone variation, and body language. You can handle objections in real time, even in a complex setting. You can plan for short and long-term situations or projects. And of course, you can create music and art or invent something new like an original idea. If you can replicate any of these human capabilities in machines, this is artificial general intelligence, or AGI. So in other words, AGI can mimic human sensory and motor skills, performance, learning, and intelligence, and use these abilities to carry out complicated tasks without human intervention. When we apply AGI to solve problems with specific and narrow objectives, we call it artificial intelligence, or AI. So let's look at some examples. AI is all around us, and you've probably interacted with AI even if you didn't realize it. Some examples of AI can be viewing an image or an object and identifying if that is an apple or an orange. It could be examining an email and classifying it spam or not. It could be writing computer language code or predicting the price of an older car. So let's get into some more specifics of AI tasks and the nature of related data. Machine learning, deep learning, and data science are all associated with AI, and it can be confusing to distinguish. So let's look at why we need AI and how it's important. AI is vital in today's world, and with the amount of data that's generated, it far exceeds the human ability to absorb, interpret, and actually make decisions based on that data. That's where AI comes in handy by enhancing the speed and effectiveness of human efforts. So, here are two major reasons why we need AI. Number one, we want to eliminate or reduce the amount of routine tasks. And businesses have a lot of routine tasks that need to be done in large numbers. So things like approving a credit card or a bank loan, processing an insurance claim, recommending products to customers are just some example of routine tasks that can be handled. And second, we as humans need a smart friend who can create stories and poems, designs, create code and music, and have humor just like us. So let's break it down further to explore some more benefits. Here are some AI domains and their examples. We have language for language translation, vision like image classification, speech like text to speech, product recommendations that can help you cross sell products, anomaly detection like detecting fraudulent transactions, learning by reward like self driven cars. You have forecasting with weather forecasting, and of course, generating content like image from text. So we're going to be exploring some of these further in the next lesson. Thank you. Let's focus on AI tasks and data pertaining to these three AI domains. We have language, audio and speech, and vision. Let's begin with language tasks. Language related AI tasks can be text related or generative AI. Text related AI tasks use text as input, and the output can vary depending on the task. Some examples include detecting language, extracting entities in a text, or extracting key phrases, and so on. Consider the example of translating text. There's many text translation tools where you simply type or paste your text into a given text box, choose your source and target language, and then click translate. Now let's look at the generative AI tasks. They are generative, which means the output text is generated by a model. Some examples are creating text like stories or poems, summarizing a text, answering questions, and so on. Let's take the example of ChatGPT, the most well-known generative chatbot. These bots can create responses from their training on large language models, and they continuously grow through machine learning. Let's look at how text as data works. Text is inherently sequential, and text consists of sentences. Sentences can have multiple words, and those words need to be converted to numbers for it to be used to train language models. This is called tokenization. Now, the length of sentences can vary, and all the sentences' lengths need to be made equal. This is done through padding. Words can have similarities with other words, and sentences can also be similar to other sentences. The similarity can be measured through dot similarity or cosine similarity. We need a way to indicate that similar words or sentences may be close by. This is done through representation called embedding. Now let's take a look at various language AI models. Language AI models refer to artificial intelligence models that are specifically designed to understand, process, and generate natural language. These models have been trained on vast amounts of textual data that can perform various natural language processing or NLP tasks. The task that needs to be performed decides the type of input and output. The deep learning model architectures that are typically used to train models that perform language tasks are recurrent neural networks, which processes data sequentially and stores hidden states, long short-term memory, which processes data sequentially that can retain the context better through the use of gates, and transformers, which processes data in parallel. It uses the concept of self-attention to better understand the context. Speech-related AI tasks can be either audio-related or generative AI. Speech-related AI tasks use audio or speech as input, and the output can vary depending on the task. For example, speech-to-text conversion or speaker recognition, voice conversion, and so on. Generative AI tasks are generative in nature, so the output audio is generated by a model. For example, you have music composition and speech synthesis. Audio or speech is digitized as snapshots taken in time. The sample rate is the number of times in a second an audio sample is taken. Most digital audio have a sampling rate of 44.1 kilohertz, which is also the sampling rate for audio CDs. This means that the audio is sampled 44,100 times per second during recording. And when the audio is played, the hardware then reconstructs the sound 44,000 times per second. The bit depth is the number of bits in each sample, or how information rich of each of those 44,000 pieces of audio is. However, nothing much can be inferred by looking at just one audio sample. Multiple samples need to be correlated to make sense of the data. For example, listening to a song for a fraction of a second, you won't be able to infer much about the song, and you'll probably need to listen to it a little bit longer. Audio and speech AI models are designed to process and understand audio data, including spoken language. These deep learning model architectures are used to train models that perform language tasks. Recurrent neural networks, long short-term memory, transformers, variational autoencoders, waveform models, and Siamese networks. All of the above models take into consideration the sequential nature of audio. Vision-related AI tasks could be image-related or generative AI. Image-related AI tasks will use an image as an input, and the output depends on the task. Some examples are classifying images, identifying objects in an image, and so on. Facial recognition is one of the most popular image-related tasks that is often used for surveillance and tracking of people in real time, and it's used in a lot of different fields, including security, biometrics, law enforcement, and social media. For generative AI tasks, the output image is generated by a model. For example, creating an image from a contextual description, generating images of a specific style or a high resolution, and so on. It can create extremely realistic new images and videos by generating original 3D models of an object, machine components, buildings, medication, people, and even more. Images as data. Images consist of pixels, and pixels can be either grayscale or color. And we can't really make out what an image is just by looking at one pixel. The task that needs to be performed decides the type of input needed and the output produced. Various architectures have evolved to handle this wide variety of tasks and data. These deep learning model architectures are typically used to train models that perform vision tasks. Convolutional neural networks, which detects patterns in images, learning hierarchical representations of visual features. YOLO, which is you only look once, processes the image and detects objects within the image. And then you have generative adversarial networks, which generates real-looking images. Some other AI tasks. Anomaly detection. This is time series data which is required for anomaly detection, and it can be a single or multivariate for fraud detection, machine failure, etc. Recommendations. You can recommend products using data of similar products or users. For recommendations, data of similar products or similar users is required. Forecasting. Time series data is required for forecasting and can be used for things like weather forecasting and predicting the stock price. Thank you.
In this lesson, I'll walk you through a couple of OCI AI services. The first one, Vision AI Service. Vision AI Service allows us to carry out a few tasks image classification, object detection, text detection, and document AI. Let us explore each one of these. So let me pick up one local file for the image analysis over here. So as you can see, the image has been analyzed and we have got multiple labels here. And this is the confidence score of those labels. So what it means is, for the vegetation, the AI service is 99.23% sure that there is a vegetation in this image. Let's try another image. This time, let's pick up an image of a zebra. So once again, you can see here that the zebra has been detected. Vegetation, grassland, plant, animal, all these labels have been assigned with the confidence scores over here. Let's pick up another image as well. Let's pick up 2 zebras this time and see what happens. So it recognizes zebra. It also assigned a label of an animal, vegetation, sky, and a mammal. Let's try object detection. Let's pick up one image of a traffic over here. So in the object detection, we essentially get all these kind of bounding boxes around the objects. And as you can see here, we have got the labels also and their confidence scores. And as you can see, multiple cars have been detected. Taxi has been detected. Multiple people have been detected into this image. Let's try another one. So it's a basket of fruit, and you can see here that multiple fruits, including orange, banana, apple, have been detected. Even a bowl has been detected over here. Let's try our text detection. So let's pick up an image of a bus over here. So as you can see, this bus has a lot of text written on it. So these are all the text that has been written and extracted by the service over here. It has even detected this number, plate M32 HOD. It has also detected this number 45 over here, all this text here, and even the text here and smaller text blocks over here also. Even this has been detected over here. Let's take another image for our text detection. So I just picked up image of different kind of fonts, and I was just curious to see if it is able to extract the text, which is written in different fonts. So this is how it goes. It basically goes line by line. So Arial, and the next word you will see is this. Then you will see Arial black and the words over here. So like that, it will keep on scanning the whole image over here. Now let's try the Document AI also. So one thing about Document AI is Document AI essentially has been moved to a separate service, which is called as Document Understanding. But from the feature perspective, the features of the Document AI Envision and the Document Understanding service are the same. So let's try one image over here. So I'll upload one receipt over here, and let's see how does it analyze that receipt. So as you can see here, this is all the raw text. First, we are able to see there's a lot more to it. So it is essentially from here like starting from receipt to thank you. It has scanned all the words over here. Now, what it has done for the key value. So what it has done is actually it has picked up the transaction date somewhere over here. And transaction time also it has picked up the subtotal. It has picked up the tags and the total. These are the standard items, so it has extracted them as a key value pairs also. And then further also line by line, you can see the key value pairs have been extracted over here. Let's see what kind of tables it has extracted. So if I just click on this drop down, the 3 tables have been extracted over here. So the first table, as you can see over here. Second table is this particular table, the total. And the third table is the bottom one here, card authorization code, and other details were like terminal ID and the amount. So I hope you find this interesting. We will explore OCI AI language service. As you can see here, we can do 2 things here. One is the text analysis, and second is text translation. So in the text analysis, all these pre-trained models, including language detection, text classification, sentiment analysis, and a few others, they are applied to a block of text that we give. So let's give some text here. Let's say we'll paste some text here and we'll analyze this text here. And we can see that the first thing it has done is it has detected the language as English. It has classified the paragraph as a science and technology or a computer-related paragraph. And it has extracted multiple entities. So entities like food and computers and manual instruments and so on. And they have been tagged as like, say, a product or an event in many other categories. And these are the confidence scores for those entities. And the key phrases for the text also have been extracted over here, say, something like the early computers or simple manual instruments and so on. The sentiments also have been detected, so aspect-based sentiment. So aspect is like one subject in the paragraph, so something like food or a service in early computers. All the sentiments have been detected, their score, and whether they are negative or positive, that has been indicated. And we also have the sentence level sentiments also, which are marked as either negative or neutral in this particular case. And the personal identifiable information has also been identified. So some of the sensitive data like World War II dates around it, and they have been indicated as potentially could be being sensitive. So that is an indication that the service has given us. That is about the text analysis. Moving on to the text translation. We have a block of text here, and the source language is English here, but we can change it to anything depending on the text that we provide. For now, let's keep it as English. And then for the target also, we have a choice of multiple languages here. Let's try the French first. So if we click Translate just in a couple of seconds, the text has been translated, and then we can try some other language like Japanese also over here. So the text has been translated into Japanese language also. And then if we go to the overview once again, we also have the capability of training the custom models also over here. If we provide the custom data, we can train our custom models also. Thanks for watching.
Hi, and welcome to this module on AI versus ML versus DL. Let's understand the difference between artificial intelligence, machine learning, and deep learning with some simple examples. Let's start with artificial intelligence, or AI. Imagine a self-driving car that can make decisions like a human driver, such as navigating traffic or detecting pedestrians, and making safe lane changes. AI refers to the broader concept of creating machines or systems that can perform tasks that typically require human intelligence. Next, we have machine learning, or ML. Visualize a spam email filter that learns to identify and move spam emails to the spam folder, and that's based on the user's interaction and email content. Now, ML is a subset of AI that focuses on the development of algorithms that enable machines to learn from and make predictions or decisions based on data. To understand what an algorithm is in the context of machine learning, it refers to a specific set of rules, mathematical equations, or procedures that the machine learning model follows to learn from data and make predictions on. And finally, we have deep learning, or DL. Think of an image recognition software that can identify specific objects or animals within images, such as recognizing cats in photos on the internet. DL is a subfield of ML that uses neural networks with many layers, deep neural networks, to learn and make sense of complex patterns in data. There are several types of machine learning, including supervised learning, unsupervised learning, and reinforcement learning. Supervised learning, where the algorithm learns from labeled data, making predictions or classifications. Unsupervised learning is an algorithm that discovers patterns and structures in unlabeled data, such as clustering or dimensionality reduction. And then you have reinforcement learning, where agents learn to make predictions and decisions by interacting with an environment and receiving rewards or punishments. Let's understand the supervised machine learning algorithm. Let's take an example of how a credit card company would approve a credit card. Once the application and documents are submitted, a verification is done, followed by a credit score check and another 10 to 15 days for approval. And how is this done? Sometimes purely manually, or by using a rules engine where you can build rules, give new data, get a decision. The drawbacks are slow. You need skilled people to build and update rules, and the rules keep changing. The good thing is that the businesses had a lot of insight as to how the decisions were made. Can we build rules by looking at the past data? Let's take a look. We all learn by examples. Past data is nothing but a set of examples. Maybe reviewing past credit card approval history can help. Through a process of training, a model can be built that will have a specific intelligence to do a specific task. The heart of training a model is an algorithm that incrementally updates the model by looking at the data samples one by one. And once it's built, the model can be used to predict an outcome on a new data. We can train the algorithm with credit card approval history to decide whether to approve a new credit card. And this is what we call supervised machine learning. It's learning from labeled data. And we're going to talk more about this in the next module. Now let's understand the unsupervised machine learning algorithm. Data does not have a specific outcome or a label as we know it. And sometimes we want to discover trends that the data has for potential insights. Similar data can be grouped into clusters. For example, retail marketing and sales. A retail company may collect information like household size, income, location, and occupation so that the suitable clusters could be identified, like a small family or a high spender, and so on. And that data can be used for marketing and sales purposes. Regulating streaming services. A streaming service may collect information like viewing sessions, minutes per session, number of unique shows watched, and so on. That can be used to regulate streaming services. Let's look at another example. We all know that fruits and vegetables have different nutritional elements. But do we know which of those fruits and vegetables are similar nutritionally? For that, we'll try to cluster fruits and vegetables' nutritional data and try to get some insights into it. This will help us include nutritionally different fruits and vegetables into our daily diets. Exploring patterns in data and grouping similar data into clusters drives unsupervised machine learning. Let's understand the reinforcement learning algorithm. How do we learn to play a game, say chess? We'll make a move or a decision, check to see if it's the right move or feedback, and we'll keep the outcomes in your memory for the next step you take, which is learning. Reinforcement learning is a machine learning approach where a computer program learns to make decisions by trying different actions and receiving feedback. It teaches agents how to solve tasks by trial and error. This approach is used in autonomous car driving and robots as well. Deep learning is all about extracting features and rules from data. Can we identify if an image is a cat or a dog by looking at just one pixel? Can we write rules to identify a cat or a dog in an image? Can the features and rules be extracted from the raw data, in this case pixels? Deep learning is really useful in this situation. It's a special kind of machine learning that trains super smart computer networks with lots of layers. And these networks can learn things all by themselves from pictures, like figuring out if a picture is a cat or a dog. Let's explore what neural networks are. To make tricky things work, we use layers of neurons. Neural networks are like a bunch of connected brain cells stacked together. They're an example of a supervised machine learning algorithm that is perhaps the best understood in the context of functional approximation. Functional approximation involves estimating a hidden function by examining past or currently known data from the specific domain. Generative AI, a subset of machine learning, creates diverse content like text, audio, images, and more. These models, often powered by neural networks, learn patterns from existing data to craft fresh and creative output. For instance, ChatGPT generates text-based responses by understanding patterns in text data that it's been trained on. Generative AI plays a vital role in various AI tasks requiring content creation and innovation.
I welcome you to this module. In this module, we will begin with foundational machine learning concepts. After that, we will dive into supervised learning, more specifically linear regression and logistic regression. Following that, we will also learn about unsupervised learning, and to end with, we will also explore and learn reinforcement learning. So let's begin. Hello and welcome to this module on machine learning foundations. In this lesson, we will learn what is machine learning, how does it work, and we will also discuss a few examples of machine learning as well. So let's begin. Machine learning is a subset of artificial intelligence that focuses on creating computer systems that can learn and predict outcomes from given examples without being explicitly programmed. It is powered by algorithms that incorporate intelligence into machines by automatically learning from a set of examples usually provided as data. Let us explore a few examples of machine learning to see what it can do for us. Machine learning is used by all of us in our day-to-day life. When we shop online, we get product recommendations based on our preferences and our shopping history. This is powered by machine learning. We are notified about movies recommendations on Netflix based on our viewing history and choices of other similar viewers. This too is driven by machine learning. While browsing emails, we are warned of a spam mail because machine learning classifies whether the mail is spam or not based on its content. In the increasingly popular self-driving cars, machine learning is responsible for taking the car to its destination. Let us see how machine learning works. Let us say we have a computer, and we need to teach the computer to differentiate between a cat and a dog. We do this by describing features of a cat or a dog. Dogs and cats have distinguishing features. For example, the body color, texture, eye color are some of the defining features which can be used to differentiate a cat from a dog. These are collectively called as input data. We also provide a corresponding output, which is called as a label, which can be a dog or a cat in this case. By describing a specific set of features, we can see that it is a cat or a dog. Machine learning model is first trained with the data set. Training data set consists of a set of features and output labels and is given as an input to the machine learning model. During the process of training, machine learning model learns the relation between input features and corresponding output labels from the provided data. Once the model learns from the data, we have a trained model. Once the model is trained, it can be used for inference. Inference is a process of getting a prediction by giving a data point. In this example, we input features of a cat or a dog, and the trained model predicts the output that is a cat or a dog label. The types of machine learning models depend on whether we have a labeled output or not. In general, there are three types of machine learning approaches. In supervised machine learning, labeled data is used to train the model. Model learns the relation between features and labels. Unsupervised learning is generally used to understand relationships within a data set. Labels are not used or are not available. Reinforcement learning uses algorithms that learn from outcomes to make decisions or choices. Let us talk about some real examples of machine learning. Some of the popular applications of supervised machine learning are disease detection, weather forecasting, stock price prediction, spam detection, and credit scoring. For example, in disease detection, the patient data is input to a machine learning model, and machine learning model predicts if a patient is suffering from a disease or not. For unsupervised machine learning, some of the most common real-time applications are to detect fraudulent transactions, customer segmentation, outlier detection, and targeted marketing campaigns. So, for example, given the transaction data, we can look for patterns that lead to fraudulent transactions. Most popular among reinforcement learning applications are automated robots, autonomous driving cars, and playing games. We will explore how supervised, unsupervised, and reinforcement machine learning works in the following lessons. Thanks for watching. Hello and welcome to this lesson on supervised learning. In this lesson, our focus will be on linear regression. Supervised learning is a machine learning model that learns from labeled data. The model learns the mapping between the input and the output. Let us talk about some typical applications that use a supervised learning model. As a house price predictor model, we input house size in square feet and model predicts the price of a house. Suppose we need to develop a machine learning model for detecting cancer. The input to the model would be the person's medical details. The output would be whether the tumor is malignant or not. If a machine learning model is developed for sentiment analysis, the input to the models would be customer reviews for products. The output would be positive, negative, or neutral sentiment labels. If a machine learning model is built for stock price prediction, the inputs would be the opening price, closing price, and volume traded. The output would be the price of the stock. Now, let us explore an example to see how the supervised training works. In supervised learning, the mapping between the input and output is a fundamental concept. It involves teaching a model to learn the relationship between input data and corresponding output or target values. Supervised learning is similar to a teacher teaching student. The model is trained with the past outcomes, and it learns the relationship or mapping between the input and output. In supervised machine learning model, the outputs can be either categorical or continuous. When the output is continuous, we use regression. And when the output is categorical, we use classification. We will discuss regression and how it is used to predict the housing prices given the house size in square feet as input. Let us see an example of house price prediction. In this scenario, we want to predict the price of a house based on a single feature, which is the size of the house in square feet. The table shows the data of house size in square feet and price in dollars. The price of the house is dependent on the size of the house. So the price is a dependent feature, and house size is an independent feature. The independent and dependent features are also called input and output. The input feature
कहा बात है भाई से पूछो ना ले वो पापड़ मान तो नगारी नगार के लाई तो बताइयो तू घर लाई तब हैं ले जा मैं लेके आई मारी दी तब आवाज ही नहीं करते यो ये नहीं तुम कहां आते हो मैंने पीछे देखे लोग ने ड्रामा ने के पीछे भी चलना करी गई
feature here is house size, and the output label is price. The single row entry of input and output is a single training example, or a tuple. This table is the training data set, which will be used for building a machine learning model. The input and output is plotted in a scatter plot, and this visualization helps in understanding the relationship between them. The graph shows that when the size of the house increases, the price also increases. If we fit a straight line that passes through these points, we can use this line for predicting the price of a house given its size. See, for example, we want to find the price of a property with size as 1,100. We can just find out the corresponding value from the scatter plot if we know the line passing through the points. Here, the relationship between house size and price is represented as a line. The slope and the bias of a line allows us to position the line to accommodate most of the data points. By changing the bias, we can move the line up and down, and by changing the slope, the line can be tilted upwards or downwards. We arrive at the best fitting line by adjusting slope and bias iteratively. The equation for this function is given by f of x equal to w multiplied by x plus b, whereas the slope of the line in b is the y-intercept. The slope in this case is the rate of change of house price with respect to the house size. Machine learning algorithm, linear regression in this case, adjusts the positioning of the line by changing the values of the weight and bias. This is done so that the difference between the actual and the predicted value is reduced. The difference between the predicted and actual value is called as error. Loss is the penalty for a bad prediction. If the model's prediction is perfect, the loss is 0. Otherwise, the loss is high. One of the ways to calculate loss is to take a difference between predicted and actual value and square it. The algorithm iteratively adjusts the weights and bias to minimize the squared loss. Once we arrive at the optimal value of the weight and bias, the model can be used for prediction. To summarize, we train a regression model by giving input and output value pairs, which we call as data set. The algorithm learns a function f, which is the mapping function. This represents a trained model. This function is used for prediction. If we give house size as input to the trained model, the learned function can predict a house price. Thanks for watching. Hello and welcome to this lesson on supervised learning. In this lesson, we will discuss how classification works. In supervised machine learning model, the output can be either categorical or continuous. When the output is continuous, we use regression to predict a numeric output. And when the output is categorical, we use classification to predict a category or a label. We have seen regression earlier while building a house price predictor. On the other hand, classification is a supervised learning problem where the goal is to assign a category or label to the outcome. If the classifier predicts whether an email is a spam or not, then it is an example of a binary classification. If we set up a model for sentiment prediction where a classifier can identify the positive, negative, and neutral sentiments in a given text, it is a multi-class classifier. Classification is a supervised machine learning technique used to categorize or assign data points into predefined classes or categories based on their features or attributes. Classifier is trained on a labeled dataset. For example, a classifier can be trained to detect a spam mail. The outcome in this case would be binary, that is, if a mail is spam or not. Let us see one simple machine learning algorithm that is used for classification. It is called as logistic regression. Logistic regression predicts if something is true or false. Let us discuss a simple model of pass or fail among a set of students given the hours of study. The input feature here is the hours of study, which is the independent variable, and the output is binary. That is pass or fail in this case. Depending on the hours of study, the student belongs to either pass class where he or she has passed the test or a failed class if he or she has failed the test. Unlike linear regression, which uses a straight line to fit the data, logistic regression uses an S-shaped curve called the sigmoid function to fit the data. The sigmoid function takes any real-valued number and squashes it into a range between 0 and 1. This property is essential for interpreting the output as a probability. In this case, we input hours of study to the sigmoid function, and we get corresponding probability of passing the test. Based on this probability, we can decide if it is a pass or fail decision. Output from the sigmoid function is to be compared with a threshold value of, say, 0.5. If output is more than 0.5, it would be classified as a pass. And if less than 0.5, it will be classified as a fail. For example, a student who studies for 6 hours and having 80% probability to pass in the test is classified as pass. A student who studies for 4 hours and have a 20% probability to pass the test is classified as fail. In the upcoming demo, we use Iris dataset. This is a standard machine learning dataset having 150 instances of 3 types of iris flowers, Iris setosa, Iris versicolor, and Iris virginica. The flowers are characterized according to 4 attributes: sepal length, sepal width, petal length, and petal width. Because there are 3 classes to be categorized on the basis of the input features, this is a case of multi-class classification. Logistic regression will be used to classify flowers in the upcoming demo. We have 4 features and an output label with 3 values representing the 3 classes. Thanks for watching. Hello and welcome again to our course on OCI Foundations. Before we start with a machine learning use case, we will first talk about a powerful tool that's a must-have in the toolbox of any aspiring data scientist. What is Anaconda? So Anaconda is an open-source distribution of Python and R for data science and machine learning. It's designed to simplify package management and deployment. So think this as a toolbox that comes preloaded with all the essential tools and libraries you will need to kick-start your journey into the world of data science and machine learning. Now, you might be wondering why to use Anaconda. Well, there are several good reasons why Anaconda is one of the most widely used data science tools. First of all is the package management. Anaconda makes it incredibly easy to install and manage data science libraries and packages. Anaconda allows you to create isolated environments for your projects. This means you can work on multiple projects with different package versions without any conflicts. A third one is this Anaconda Navigator itself, a very user-friendly interface to manage your environments, install packages, and launch Jupyter Notebooks all without needing to use the command line. And again, this is a cross-platform tool. So whether you are using Windows, Mac, or Linux, Anaconda is available for all major operating systems. The one tool in particular, which we are going to use for our machine learning use case, is this Jupyter Notebook. Jupyter Notebook is a powerful, interactive development environment, which we usually call IDE, that allows you to create and share documents containing live code equations, visualizations, and narrative text. This is a very fantastic tool for prototyping data exploration and creating interactive presentations. Let's launch this. And our Jupyter Notebook server is launched in your local machine, and you will see a tab in your browser similar to this here. You can see 2 tabs here, Files and Running. Files will show you all existing files and folders, and Running will show you your existing terminals or notebooks. Third tab here are Clusters. This is for parallel processing, but again, it's out of scope for this demo. So going back to your files, let's create a new folder. There is a folder called Untitled just created seconds ago. Click on that and rename it. And we will just call it ML Demo. Anaconda is an open-source distribution of Python and R for data science and machine learning. It's designed to simplify package management and deployment. So think this as a toolbox that comes preloaded with all the essential tools and libraries you will need to kick-start your journey into the world of data science and machine learning. Now, you might be wondering why to use Anaconda. Well, there are several good reasons why Anaconda is one of the most widely used data science tools. First of all is the package management. Anaconda makes it incredibly easy to install and manage data science libraries and packages. Anaconda allows you to create isolated environments for your projects. This means you can work on multiple projects with different package versions without any conflicts. A third one is this Anaconda Navigator itself, a very user-friendly interface to manage your environments, install packages, and launch Jupyter Notebooks all without needing to use the command line. And again, this is a cross-platform tool. So whether you are using Windows, Mac, or Linux, Anaconda is available for all major operating systems. The one tool in particular, which we are going to use for our machine learning use case, is this Jupyter Notebook. Jupyter Notebook is a powerful, interactive development environment, which we usually call IDE, that allows you to create and share documents containing live code equations, visualizations, and narrative text. This is a very fantastic tool for prototyping data exploration and creating interactive presentations. Let's launch this. And our Jupyter Notebook server is launched in your local machine, and you will see a tab in your browser similar to this here. You can see two tabs here, Files and Running. Files will show you all existing files and folders, and Running will show you your existing terminals or notebooks. Third tab here are Clusters. This is for parallel processing, but again, it's out of scope for this demo. So going back to your files, let's create a new folder. There is a folder called Untitled just created seconds ago. Click on that and rename it. And we will just call it ML Demo. Okay, so we have our folder created. So if you double click on that folder, it says the notebook list is empty. Let's create a new notebook. I have this Python 3 kernel. Click on that. Clicking on that took me to this new tab, which is a notebook where we will write our codes. First, rename this to ML Demo 1. And you can do just by simply clicking on this Untitled, ML Demo 1. Clicking on that took me to Python 3 kernel. Let's create a new notebook. I have this Python 3 kernel. Click on that. Clicking on that took me to this new tab, which is a notebook where we will write our codes. First, rename this to ML Demo 1. And you can do just by simply clicking on this Untitled, and I will name it ML Demo 1. Click on Rename, and you will see now it renames this Jupyter Notebook. So now let's write a few lines of Python code, and let's see how this cell works actually. To comment, you start with a hash. So I'm going to write this program, adds two numbers, okay. So I will create my first variable number 1. Number 2, let's take 4. And I will add another comment. Add two numbers. And I will write another variable sum and write num1 plus num2. You can either run it from here, or you can also click Shift-Enter on your keyboard. You can also press Shift-Enter on your keyboard, and this will run this cell. In the next cell, I will display the sum, and I will write a print statement. The sum of, let's say, 0 and 1 is 2, format num1, num2, and sum. On running this cell, you can see the result. So this is our very basic Python code. The sum of 1 and 4 is 5. This is how you run any code in your cell. So now we will start with our first demo. Before we implement a machine learning use case, let's revisit a typical machine learning process, which involves loading of the data, preprocessing the data, training a model, evaluating the model, and making predictions. Machine learning process. I'll convert it to Markdown. The code which we will write will demonstrate a simple machine learning workflow using logistic regression, which is a classifier. In machine learning, a classifier is a type of algorithm or model that is used for the task of classification. Classification is a supervised learning problem where the goal is to assign a category or label to a given input based on its features. Again, the primary purpose of a classifier is to learn patterns and relationships in the training data so that it can make predictions or decisions about the category or label of new unseen data points. Our code will load the data, will prepare it for training, will train a model, and will make prediction and print the results. The example which we will be using is a very foundational example of how machine learning models are built and used for classification tasks. So let's begin. We will start with importing some Python and ML libraries, which we will need to run codes. Let's first import some libraries. Now I will add a comment, import necessary libraries. Okay. So the first line here, this line imports the pandas library and aliases it as a PD. Pandas is used for data manipulation and provides data structures like data frames and series for handling data efficiently. The second line, this imports the logistic regression class from scikit-learn or sklearn library. This scikit-learn is a popular machine learning library that provides tool for data preprocessing, model training, and evaluation. If you run this cell, you might not be able to successfully import these libraries if these are not the part of your kernel. And to install these libraries to your notebook kernel, go back to your previous page. And in the new item Open a Terminal, this page will pop up here. And then on this page, you can copy-paste this particular command. I copied it from the installation section from this package's scikit-learn. So conda install -c anaconda scikit-learn. If all goes well, you will see a page like this. And this will prepare or verify and execute your transaction, and will add that library to your kernel. Once I run this code, we have successfully imported all the necessary libraries. Next, we will load our data set. We will load the data set and display the first few rows. We use pandas to read a CSV file named iris.csv and store it in a data frame called iris_data. This line loads the data set into memory and making it available for analysis. This data set, often called the iris data set, contain information about different species of iris flowers. And this is how the iris.csv file looks. So you can see it has different columns, the attributes. If we run this code, now you can see the same iris_data data frame shows the first 5 rows on running this particular line. A head method is used to inspect the data set and get a quick overview of its content. This is a very helpful step to understand the structure of your data. In the next step, we will split the data into features X and label why the features denoted as X contains the attributes of the iris flowers, while the labels denoted as Y represents the species of the iris. So we also got rid of the ID, this column, which is not a useful attribute for the flower. It's just a numbering for our rows. In this line, we create a new data frame, as I said, X, by dropping the ID and species column from iris_data. And the next line, we're going to create a series Y that contains the species columns from the iris_data data frame. This represents the target variable of labels. Let's run this cell. You can also check how those looks. So X looks like X is a data frame and Y is a series, so which will have the corresponding target levels for each of these rows. In the next step, we will create a machine learning model. So as I discussed about logistic regression, this is a classifier. In this demo, we will initialize it as model equals logistic regression method using this logistic regression class we imported earlier. This line initializes the model with default settings. Next will come the training part. So in this step, we will train our model. This fit method is called to train the logistic regression model on features X and their corresponding labels, why this step involves learning the relationship between the features and the target variable. So let's run this code. Once our model is trained, next comes the predictions. So let's make prediction on a few data points. You can see these data points here. This will act as an attribute for, let's say, unseen data. Okay, let's run this cell. Now let's print the prediction to the console. This line here will display the predicted species of iris flower based on these given input feature values. The predictions on the basis of these inputs came out to be Iris setosa. So in this demo, we loaded a data set, we split it into features and labels, created a machine learning model, trained that model, and use it to make predictions and print those predictions on our console. So I hope this demo will be helpful, and now we will move on to the next demo. First of all, I'm going to make a duplicate of this existing file and will rename it as ML-demo. So click on this duplicate. And then I can rename this as 2. Since we are not going to use this notebook anymore, I can close the tab and shut down. Let's open ML-demo 2. In this new notebook, let's start by adding few more libraries which we need. Before that, click on the kernel. Restart and clear all the output. Let's import the libraries, which we will need for this section of the demo. We have imported NumPy library and aliased it as a NP. NumPy is used for numerical computations and provides arrays and mathematical functions. Again, we have imported a train test split function from scikit-learn model selection module. So this function is used to split the data set into training and testing sets. We have imported the standard scalar class from the scikit-learn's preprocessing module. So this class is used to standardize the features by scaling them to have a mean of 0 and standard deviation of 1. We import the accuracy score function from scikit-learn's metrics module. So this function is used to calculate the accuracy of model predictions. So let's understand what these libraries are exactly doing. Let's take the case of this standardization. Standardization is the process of transforming data so that it has mean of 0 and a standard deviation of 1. It's important in machine learning because it ensures that all features or variables are on the same scale, preventing some features from dominating the learning process due to their largest magnitude. For example, let's say you are building a machine learning model to predict house prices, and you have two features, square footage and number of bedrooms. The square footage values, let's say it ranges from 1,000 to 5,000 square feet, while the number of bedrooms ranges from 1 to 6. So in case if you don't standardize these features, the model might give more weight to a square footage because it has larger values. And this could result in an inaccurate model, as the number of bedrooms might also be a significant predictor. So the standardization scales both those features to have comparable means and standard deviation, and hence, allowing the model to treat them equally. Coming on to this train-test split, this is helpful to divide the data into a training set and a test set. And now you can train your model on the training set and evaluate its accuracy on the testing set. This accuracy score here, this is a metric used to measure the accuracy of a classification model. It calculates the ratio of correctly predicted instances to the total number of instances in the data set. This is an important part of validation, which is the process of evaluating a machine learning model's performance on a separate data set, which we call as validation set to ensure it generalizes well and does not overfit the training data. To explain this, for example, let's say you are building a spam email classifier, which will basically classify your email as spam or not spam. So after training your model, you use a validation set. Usually, the email is not seen during the training process to calculate the accuracy using this accuracy score. If accuracy is 95%, it means your model correctly classifies 95% of email as a spam or not spam. So the validation overall ensures your model performs well on the new unseen data and helps you avoid building a model that only works on the training data. And that latter case is called as overfitting. Following the previous demo, we will now load the data set and display some rows and split the data set into feature X and labels Y. These libraries have been successfully imported. So now we will run the next 2 consecutive cells. As the next step, we will further split the data into training and test sets, meaning we will have X divided into X-train, X-test, and Y divided into Y-train and Y-test. So let's paste the code for the same. You also notice that there is a parameter called random state, so this parameter is often used to control the randomness. So what I mean by that when you use this train test split from sklearn and set random state, for example, equals to 42, the data splitting will be random, but reproducible. So if you run the same code with same random state value again, you will get the same split of the data. And this is useful for the reproducibility and for comparing results between different experiments. So let's now run this cell block. We will now standardize our features. So we will add a cell here. This is the code for standardization of the features. In the first line, we are creating an instance of the standard scalar class, which will be used to standardize the features. Next, we'll follow the same code as previously we did. We will create an ML model, so we'll create an instance of logistic regression model. But now in the next step, instead of you just training the model on X and Y, we will use the newly scaled data using this fit method. So let's replace this code. So now on running this code, we have trained the logistic regression model using the standardized training features X-train skill and the corresponding training labels Y-train. Model learns the relationship between the features and the labels during this step. Once trained before predicting the values, let's evaluate our model on the testing set. So basically, let's see how our model is performing on the unseen data once it has learned the patterns from the training data. Here, we have used the train model to make predictions on the standardized testing features, which is X-test scale, and this line produces a set of predicted labels for this testing data. We will calculate the accuracy of the model's predictions by comparing this predicted labels with the true labels from the testing set. The accuracy score function provides the accuracy as a metric. Generally speaking, higher the accuracy score is, that means your model is better. So we have got the accuracy of 1. That means this is 100% accurate. We will create a sample new data for the prediction. So this is the code for creating a sample new data for prediction using NumPy. I will assume that these data points represent the attributes of iris flowers, which we want to classify. It can be entirely new data points or examples for which we want to predict the species. The sepal length is this first column. The sepal width is this next column. This petal length and petal width is again respectively the other two columns. And then what we are trying to do here, guess the species. And this is a new data for prediction. The model haven't seen this data yet. We will again start with standardizing this new data samples. This is the code. Let me run the cell block. We have standardized the new data in the same way that we did for the training and testing data. Let's make predictions. Squad will help you to make predictions, and we use the trained models to make predictions on the standardized new data points. The model will now predict the species of iris flower based on their attributes. I will display the predicted classes on the basis of this sample new data. Let's run this cell and you can see that these are the respective predicted classes as per this sample new data for prediction. The first attributes combination, this has been classified as iris setosa, and similarly, for the other two, it is classified as iris virginica and iris setosa again. This extended demo, we covered all the additional steps, such as off-data preprocessing, some model evaluation, and making predictions on the new data. Again, this reflects a more comprehensive machine learning workflow. As you continue to explore machine learning, you will find that these steps are crucial for building effective models. This concludes our demo. I hope it will be helpful for your future endeavors in machine learning, so thank you for joining. In this lesson, we will learn about unsupervised machine learning. Unsupervised machine learning is a type of machine learning where there are no labeled outputs. The algorithm learns the patterns and relationships in the data and groups, similar data items. In unsupervised machine learning, patterns in the data are explored without being explicitly told what to look for. For example, if you give a set of different colored Lego pieces to a child and ask them to sort the pieces, they may group the Lego pieces based on any patterns they observe. These could be groups of the same color, size, or type. Similarly, in unsupervised learning, we group unlabeled data sets. One more example could be, say, imagine you have a basket of various fruits, say apples, bananas, and oranges, and your task is to group these fruits based on their similarities. You observe that some fruits are round and red, while others are elongated and yellow. Without being told explicitly, you decide to group the round and red fruits together as one cluster, and the elongated and yellow fruits as another cluster. There you go. You have just performed an unsupervised learning task. Clustering is a method of grouping data items based on similarities. Within a cluster, the data items are more similar than the items outside the cluster. If some data items do not fall within any cluster, these data items are deemed as outlier points. For example, grapes do have a different shape, size, and color as of apple, pears, and strawberry, and hence could be an outlier. Having seen what clustering is, let us explore some of its important use cases. The first use case of unsupervised machine learning is market segmentation. In market segmentation, one example is providing the purchasing details of an online shop to a clustering algorithm. Based on the items purchased and purchasing behavior, the clustering algorithm can identify customers based on the similarity between the products purchased. For example, customers with a particular age group who buy protein diet products can be shown an advertisement of sports-related products. The second use case is on outlier analysis. One typical example for outlier analysis is to provide credit card purchase data for clustering. Fraudulent transactions can be detected by a bank by using outliers. In some transaction, amounts are too high or recurring, it signifies an outlier. The third use case is recommendation systems. An example for recommendation systems is to provide users movie viewing history as input to a clustering algorithm. It clusters users based on the type or rating of movies they have watched. The output helps to provide personalized movie recommendations to users. For example, Netflix. The same applies for music recommendations also. Let us explore the steps involved in unsupervised machine learning. Before that, we need to understand the concept of similarity. Similarity is how close two data points are to each other and is a value between 0 and 1. Similarity between objects decide which cluster they will fall into, and hence, important for clustering. Now suppose from a basket of fruits we need to identify similar fruits. We can do it, say, based on color. Then apple and cherry are similar to each other based on color. More the similarity between objects, the closer is the value to 1. So for apple and cherry, in this case, similarity would have a value closer to 1. There are various types of similarity measures used in clustering. Let us look at the steps involved in supervised learning to see how similarity metrics are used. Just like supervised learning, unsupervised learning also follows a workflow to cluster. The data, for example, the fruits data, the following steps are followed. Prepare the data. While preparing the data, the basic preprocessing steps like removing missing values, normalizing the data, and feature scaling are performed. Create similarity matrix. The choice on which similarity matrix to use depends on the nature of the data and the specific clustering algorithm being used. Some common similarity metrics which are frequently used are Euclidean distance metric, Manhattan distance metric, cosine similarity matrix, and Jaccard similarity matrix. Run the clustering algorithm. Clustering algorithms use similarity matrix to cluster the data. The different types of clustering algorithms are partition-based, hierarchical-based, density-based, and distribution-based. Interpret the results and adjust your clustering. Checking the quality of your clustering output is iterative and exploratory. Because there is no labeled output, clustering lacks the ground truth that can verify the output. Verify the results against expectations at the cluster level and the example level. Improving the result requires iteratively experimenting with the previous steps to see how they affect the clustering. Thanks for watching. In this lesson, we will learn about reinforcement learning. Reinforcement learning is like teaching a dog new tricks. You reward it when it does something right, and over time, it learns to perform these actions to get more rewards. More formally, reinforcement learning is a type of machine learning that enables an agent to learn from its interaction with the environment, while receiving feedback in the form of rewards or penalties without any labeled data. Let us look at some examples. Reinforcement learning is more prevalent in our daily lives than we might realize. To name a few, autonomous vehicles, the development of self-driving cars and autonomous drones rely heavily on reinforcement learning to make real-time decisions based on sensor data, traffic conditions, and safety considerations. Smart home devices. Virtual assistants like Alexa, Google Assistant, and Siri utilize reinforcement learning to improve natural language processing and adapt to individual users' speech patterns and preferences. Industrial automation. In manufacturing and production processes, reinforcement learning is applied to optimize the performance of robots and control systems, leading to improved efficiency and reduced service. Gaming and entertainment. Many video games, virtual reality experiences, and interactive entertainment use reinforcement learning to create intelligent and challenging computer-controlled opponents. The AI characters in games learn from player interactions and become more difficult to beat as the game progresses. Let us take an example to discuss common terminology. Let us say we want to train a self-driving car to drive on a road and reach its destination. For this, it would need to learn how to steer the car based on what it sees in front through a camera. In this example, car and its intelligence to steer on the road is called as an agent. More formally, agent is a learner or decision maker that interacts with the environment, takes actions, and learns from the feedback received. Environment, in this case, is the road and its surroundings with which the car interacts. More formally, environment is the external system with which the agent interacts. It is the world or context in which the agent operates and receives feedback for its actions. In this example, what we see through a camera in front of a car at a moment is a state. More formally, state is a representation of the current situation or configuration of the environment at a particular time. It contains the necessary information for the agent to make decisions. The actions in this example are to drive left or right or keep straight. Formal definition of actions. Actions are a set of possible moves or decisions that the agent can take in a given state. Actions have an impact on the environment and influence future states. After driving through the road many times, the car learns what action to take when it views a road through the camera. This learning is a policy. Formally, policy is a strategy or mapping that the agent uses to decide which action to take in a given state. It defines the agent's behavior and determines how it selects actions. Consider the example of training a dog to learn tricks like pick up a ball, roll, sit, and so on. Here the dog is an agent, and the place it receives training is the environment. While training the dog, you provide a positive reward signal if the dog picks it right, and a warning or punishment if the dog does not pick up a trick. In due course, the dog gets trained by the positive rewards or negative punishments. The same tactics are applied to train a machine in the reinforcement learning. For machines, the policy is the brain of our agent. It is the function that tells what actions to take when in a given state. The goal of reinforcement learning algorithm is to find the policy that will yield a lot of rewards for the agent if the agent follows that policy, referred to as the optimal policy. Through a process of learning from experiences and feedback, the agent becomes more proficient at making good decisions and accomplishing tasks. This process continues until eventually we end up with the optimal policy. The optimal policy is learned through training by using algorithms like deep Q-learning or Q-learning. Let us explore this a little more with another example. Reinforcement learning can be used in a robotic arm to optimize the process of placing goods in a warehouse. The goal is to teach the robotic arm how to pick up items and place them efficiently and accurately in the desired locations within the warehouse. Let us see how a robotic arm gets trained using reinforcement learning. The first step is setting the environment. This includes the robotic arm, the warehouse layout, the goods to be placed, and the target locations for each item. The second step is to define state representations. For the robotic arm, the state can include information such as the position and orientation of the arm, the position of the items to be picked up, and the positions of the target locations. Next is action space. Define the action space. Action spaces are the possible actions the robotic arm can take in each state. Decide rewards and penalty. The robotic arm should be rewarded when it successfully places an item in the correct location and penalized for dropping items, damaging goods, or failing to place items accurately. In training, the robotic arm starts in a random state and takes actions in the environment. Initially, it explores different actions randomly and observes the rewards and penalties it receives for each action. As it learns, it starts to prioritize actions that lead to higher rewards and avoids actions that result in penalties. Through multiple training iterations, the robotic arm learns better strategies for picking up and placing items in the warehouse. Thanks for watching.
Hello, my name is Hemant, and I'm a Senior Principal Training Lead at Oracle University. I welcome you to this module. In this module, we will begin with foundational concepts in deep learning. Following that, we will also discuss neural network architectures which are suitable for image analysis. And following that, we will also discuss neural network architectures that are suitable for sequence problems. So let us begin. In this lesson, we will learn about deep learning. So let's begin. Deep learning is a subset of machine learning that focuses on training artificial neural networks to solve a task at hand, say, for example, image classification. A very important quality of the ANN is that it can process raw data like pixels of an image and extract patterns from it. These patterns are treated as features to predict the outcomes. Let us say we have a set of handwritten images of digits 0 to 9. As we know, everyone writes the digits in a slightly different ways. So how do we train a machine to identify a handwritten digit? For this, we use ANN. ANN accepts image pixels as inputs, extract patterns like edges and curves and so on, and correlates these patterns to predict an outcome, that is, what digit does the image has in this case. In short, given a bunch of pixels, ANN is able to process pixels data, learn an internal representation of the data, and predict outcomes. We need to specify features while we train machine learning algorithm. With deep learning, features are automatically extracted from the data. Internal representation of features and their combinations is built to predict outcomes by deep learning algorithms. This may not be feasible manually. Deep learning algorithms can make use of parallel computations. For this, usually, data is split into small batches and processed parallelly. So these algorithms can process large amount of data in a short time to learn the features and their combinations. This leads to scalability and performance. In short, deep learning complements machine learning algorithms for complex data for which features cannot be described easily. Let us quickly look at the history of deep learning. Some of the deep learning concepts like artificial neuron, perceptron, and multilayer perceptron existed as early as 1950s. One of the most important concepts of using backpropagation for training and came in 1980s. In 1990s, convolutional neural network were also introduced for image analysis tasks. Starting 2000, GPU were introduced, and 2010 onwards, GPU became cheaper and widely available. This fueled the widespread adoption of deep learning uses like computer vision, natural language processing, speech recognition, text translation, and so on. In 2012, major networks like AlexNet and DeepQ Network were built. 2016 onward, generative use cases of the deep learning also started to come up. Today, we have widely adopted deep learning for a variety of use cases, including large language models and many other types of generative models. Deep learning algorithms are targeted at a variety of data and applications. For data, we have images, videos, text, and audio. For images, applications can be image classification, object detection, and so on. For textual data, applications are to translate the text or detect a sentiment of a text. For audio, the applications can be music generation, speech to text, and so on. Selecting the right deep learning algorithm based on the data and application is important. For image tasks like image classification, object detection, image segmentation, or facial recognition, CNN is a suitable architecture. For text, we have a choice of the latest transformers or LSTM or even RNN. For a generative task like text summarization, question answering, transformers is a good choice. For generating images, text-to-image generation, transformers, GANs, or division models are available choice. So let us understand what is artificial neural network or ANN. Artificial neural networks are inspired by the human brain. They are made up of interconnected nodes called as neurons. Let us get a simplified understanding of how inputs are processed by a neuron. In ANN, we assign weights to the connection between neurons. Weighted inputs are added up, and if the sum crosses a specified threshold, the neuron is fired, and the outputs of a layer of neuron become an input to another layer. Let us also understand the building blocks of ANN. So first building block is layers. We have input layer, output layer, and multiple hidden layers. The input layer and output layer are mandatory, and the hidden layers are optional. The second unit is neurons. Neurons are computational units which accept an input and produce an output. Weights determine the strength of connection between neurons. So the connection could be between input and a neuron, or it could be between neuron and another neuron. Activation functions work on the weighted sum of inputs to a neuron and produce an output. Additional input to the neuron that allows a certain degree of flexibility is called as a bias. Now, having understood the components of the ANN, let's also take one small example and see how to train and to recognize handwritten digits from images. For that, we have to collect a large number of digit images, and we need to train ANN using these images. Now let us see how do we train ANN using images. So in this case, the images consist of 28 by 28 pixels, which act as input layer. For the output, we have neurons, 10 neurons, which represent digits 0 to 9, and we have multiple hidden layers. So in this case, we have 2 hidden layers which are consisting of 16 neurons each. The hidden layers are responsible for capturing the internal representation of the raw image data, and the output layer is responsible for producing the desired outcomes. So in this case, the desired outcome is the prediction of whether the digit is 0 or 1 or up to digit 9. So how do we train this particular? So the first thing we use is the backpropagation algorithm. During training, we show an image to the ANN. Let us say it is an image of digit 2. So we expect output neuron for digit 2 to fire. But in real, let us say output neuron of a digit 6 fired. So what do? We know that there is an error. So to correct an error, we adjust the weights of the connection between neurons based on a calculation, which we call as backpropagation algorithm. By showing thousands of images and adjusting the weights iteratively, ANN is able to predict correct outcome for most of the input images. This process of adjusting weights through backpropagation is called as model training. Thanks for listening. In this lesson, we will learn about deep learning models that are suitable for processing sequential data, for example, a paragraph of a text. Sequence models are used to solve problems where the input data is in the form of sequences. The sequences are ordered lists of data points or events. The goal in sequence models is to find patterns and dependencies within the data and make predictions, classifications, or even generate new sequences. Some common examples of the sequence models are, in natural language processing, deep learning models are used for tasks such as machine translation, sentiment analysis, or text generation. In speech recognition, deep learning models are used to convert recorded audio into text. And deep learning models can generate new music or create original compositions. Even sequences of hand gestures are interpreted by deep learning models for applications like sign language recognition. In fields like finance or weather prediction, time series data is used to predict future values. Let us see some of the deep learning models which can be used to work with sequence data. Recurrent neural networks, abbreviated as RNN, are a class of neural network architectures specifically designed to handle sequential data. Unlike traditional feed-forward neural network, RNN have a feedback loop that allows information to persist across different time steps. The key features of RNN is their ability to maintain an internal state, often referred to as a hidden state or memory, which is updated as the network processes each element in the input sequence. The hidden state is then used as input to the network for the next time step, allowing the model to capture dependencies and patterns in the data that are spread across time. There are different types of RNN architecture based on application. One of them is one-to-one. This is like feed-forward neural network and is not suited for sequential data. A one-to-many model produces multiple output values for one input value. Music generation or sequence generation are some applications using this architecture. A many-to-one model produces one output value after receiving multiple input values. Example is sentiment analysis based on the review. Many-to-many model produces multiple output values for multiple input values. Examples are machine translation and named entity recognition. RNN does not perform that well when it comes to capturing long-term dependencies. This is due to the vanishing gradients problem, which is overcome by using LSTM model. Long short-term memory, abbreviated as LSTM, works by using a specialized memory cell and a gating mechanisms to capture long-term dependencies in the sequential data. The key idea behind LSTM is to selectively remember or forget information over time, enabling the model to maintain relevant information over long sequences, which helps overcome the vanishing gradients problem. Let us see how LSTM works. Let us see the step-by-step working of LSTM. At each time step, the LSTM takes an input vector representing the current data point in the sequence. The LSTM also receives the previous hidden state and cell state. These represent what the LSTM has remembered and forgotten up to the current point in the sequence. The core of the LSTM lies in its gating mechanisms, which include 3 gates: the input gate, the forget gate, and the output gate. These gates are like the filters that control the flow of information within the LSTM cell. The input gate decides what new information from the current input should be added to the memory cell. The forget gate determines what information in the current memory cell should be discarded or forgotten. The output gate regulates how much of the current memory cell should be exposed as the output of the current time step. Using the information from the input gate and forget gate, the LSTM updates its cell state. The LSTM then uses the output to produce the current hidden state, which becomes the output of the LSTM for the next time step. Thanks for watching. Welcome to a new lesson. In this lesson, we will learn about convolutional neural networks, abbreviated as CNN. Let us get an overview of deep learning model architectures. The first one is feed-forward neural networks, abbreviated as FNN. This is also called as multilayer perceptron as MLP and is the simplest form of neural networks. Second is CNN, which is convolutional neural network. This can automatically detect and learn local patterns and features in images and videos. The third one is RNN, which is a recurrent neural network. RNN are designed to handle sequential data, such as time series data or natural language. They have a feedback loop that allows them to maintain hidden states and capture temporal dependencies. The fourth one is autoencoders. Autoencoders are unsupervised learning models used for feature extraction and dimensionality reduction, and is commonly employed in data compression and anomaly detection. The fifth one is LSTM, that is long short-term memory. LSTM is a specialized RNN variant designed to handle long-term dependencies in sequential data. The sixth one is GAN, which is generative adversarial network. This is a powerful deep learning model which is used for generating realistic synthetic data such as images, audio, and text. And the last one is transformers. Transformers are widely used in natural language processing and have become state-of-the-art models for tasks like machine translation, text generation, and language understanding. In this lesson, we will go deeper into the understanding of CNN. So what is a convolutional neural network? CNN is a type specifically designed for processing and analyzing grid-like data such as images and videos. In the ANN, which was seen in the previous lesson, the input image is converted to a single-dimensional array and given as an input to the network. But that does not work well with the image data because image data is inherently two-dimensional. CNN works better with two-dimensional data. The role of the CNN is to reduce the image into a form which is easier to process and without losing features which are critical for getting a good prediction. Let us see how this happens using a CNN architecture. Let us get an overview of the CNN layers. The first one is input layer. Input layer is followed by feature extraction layers, which is a combination and repetition of multiple feature extraction layers, including convolutional layer with ReLU activation and a pooling layer. And this is followed by a classification layer. These are the fully connected output layers where the classification occurs as output classes. The feature extraction layers play a vital role in image classification. Let us see what happens in that layer with an example. In order to understand feature extraction layers better, let us take an analogy. Let us say we have a robot to inspect a house and tell us what type of a house it is. It uses many tools for this purpose. The first tool is a blueprint detector. It scans different parts of the house like walls, floors, or windows and looks for specific patterns or features. The second tool is a pattern highlighter. This tool marks areas detected by the blueprint detector. The next tool is a summarizer. It tries to capture the most significant features of every room. The next tool is House Expert, which looks at all the highlighted patterns and features and tries to understand the kind of the house. The next tool is a guess maker. It assigns probabilities to the different possible house types. And finally, the quality checker randomly checks different parts of the analysis to make sure that the robot doesn't rely too much on any single piece of information. Let us see how this is mapped to the feature extraction layers. Let us check the analogy between a robot house inspector and different layers of the feature extraction. Similar to Blueprint Detector, we have a convolutional layer. This layer applies convolutional operations to the input image using small filters known as kernels. Each filter slides across the input image to detect specific features, such as edges, corners, or textures. Similar to Pattern Highlighter, we have an activation function. The activation function allows the network to learn more complex and nonlinear relationships in the data. Pooling layer is similar to Room Summarizer. Pooling helps reduce the spatial dimensions of the feature maps generated by the convolutional layers. Similar to a house expert, we have a fully connected layer, which is responsible for making final predictions or classifications based on the learned features. Softmax layer converts the output of the last fully connected layers into probability scores. The class with the highest probability is the predicted class. This is similar to the guessmaker. And finally, we have the dropout layer. This layer is a regularization technique used to prevent overfitting in the network. This has the same role as that of a quality checker. To summarize, the purpose of feature extraction layers is to automatically learn and extract relevant patterns and features from the input images. Convolutional layer applies convolutional operations to the input image using small filters known as kernels. Each filter slides across the input image to detect specific features, such as edges, corners, or textures. The second one is the activation function, which is applied after each convolutional operation. The activation function allows the network to learn more complex and nonlinear relationships in the data. And the third one is pooling. It helps reduce computational complexity and also reduces the spatial dimensions of the feature maps generated by the convolutional layers. CNN do have some limitations that are important to be aware of. Training CNN on large data sets can be computationally expensive and time-consuming. CNN are susceptible to overfitting, especially when the training data is limited or imbalanced. CNN are considered black box models, making it difficult to interpret. And CNN can be sensitive to small changes in the input leading to unstable predictions. One of the most widely used applications of CNN is image classification. For example, classifying whether an image contains a specific object, say, cat or a dog. CNN are used for object detection tasks. The goal here is to draw bounding boxes around objects in an image. CNN can perform pixel-level segmentation, where each pixel in the image is labeled to represent different objects or regions. CNN are employed for face recognition tasks as well, identifying and verifying individuals based on facial features. CNN are widely used in medical image analysis, helping with tasks like tumor detection, diagnosis, and classification of various medical conditions. CNN play an important role in the development of self-driving cars, helping them to recognize and understand the road traffic signs, pedestrians, and other vehicles. And CNN are applied in analyzing satellite images and remote sensing data for tasks such as land cover classification and environmental monitoring. Thanks for watching. In this demonstration, we will see how deep learning is useful to separate complex set of data points. So for that, we begin with creating our data set using Make Circles in Sklearn library. So this is how a set of data point looks like. So we have an outer circle generated with the label 0. We have an inner circle generated with the label of 1. And we want to train a classifier to separate these two sets of data points. So once we have trained a classifier, and if we create a point somewhere here in this region, we expect that the classifier will be able to label it as 1. And if we generate a point and give it to a classifier, we expect that the classifier will be able to classify it as a label 0. So let us discuss some of the parameters of the Make Circles. So first of all, we have n samples is 300. So we have totally 300 data points, 150 of which are red data points, and 150 are green data points. We are also adding some noise to the generation of the data points. Factor 0.5 decides how far the two concentric circles are going to be. And the random state will be used as a seed for the generation of data points. So let's change some of these parameters. So we have changed this parameter, and we will rerun this. So as we can see, the number of points are lesser now. Let's roll back to our 300, and let's increase the noise here. So as you can see here, the distribution of the points has become more random because we added more noise to it. So let's roll back to 0.1 and let's use a factor 2, say 0.7. So we can see that the distance between the two concentric circles has reduced. Now that we have created our data points, let us see how our classifier works. As we discuss, multi-layer perceptron can have multiple hidden layers, and each of the layer can have multiple neurons. So we begin with number of neurons as 1. As we can see here with the number of neurons as 1, the classifier has predicted all the points as class 0. So in this case, the classifier is not working well. Let us change the number of neurons to 2. As we can see here, some of the data points are predicted correctly. Some of the green points are predicted as red, and some of the red points are predicted as green. Let's change the number of neurons to 3. As we can see, the decision boundary has become complex and more number of points are classified correctly. Let's increase the number of neurons to 4. We can see that the decision boundary has become more complex and more accurate, and more number of points are predicted correctly. So similarly, if we increase the number of neurons to 5 and 6, we can see that the decision boundary becomes more complex and more accurate, and more number of points are predicted accurately. Now that we understand how our classifier works, let me walk you through the code. The hidden layer size slider that we see in the plot of points is created using Interactive Widget. We pass in the function that will be called every time a slider value is updated, and the new hidden layer size is passed to the function. Now let us see how update plot function is implemented. We have already created our data set, which consists of an array of data points and 0 or 1 labels. Each data point has an x-coordinate value and a y-coordinate value. Next, we create MLP classifier. We create MLP classifier with only one layer that has multiple neurons. The number of neurons is set to the hidden layer size. We also pass in a ReLU activation function. This will help creating nonlinear boundaries. The classifier will be trained until it reaches the maximum iterations. Random state will help initialize weights and biases. Next, we train our classifier using the data points and labels. Once the classifier is trained, we can use it to predict labels for new data points. Now we need a new set of data points that cover the range of data set we use for training. For that, we create a set of 100 x and y coordinates in the range of training data points. Next, we reshape these x and y coordinates in the shape of 100 by 100 grid. Next, we combine these grids to get our new data points, which we will use for predicting labels. The predicted labels are reshaped so that these can be used for plotting the decision boundary. We also predict labels for training data points so that we can show these on the plot, along with the decision boundary. Finally, we use contour method to plot the decision boundary, which shows how points with predicted labels 0 and 1 are separated. We also plot data points with label 0 in red color and label 1 in green color. And finally, we plot the X and Y labels and the title of the plot. And we display the plot. Thanks for watching.
Welcome to this module on generative AI and large language model fundamentals. In this module, we will first look at what exactly is generative AI. Then we will look into the large language models, what they are, and how do they actually work. Large language models are based on a deep learning architecture called transformers, and we have a two-part series where we dive deeper into transformers. Then we look at the two fundamental ways you interact with large language models, that is, using prompts and fine tuning. And then finally, we conclude this module by looking at ways you can customize LLMs to work with your own data. There is a lot to unpack, so let's get started. Welcome to an introduction to generative AI lesson. So, what is AI? AI is the ability of machine learnings to imitate human intelligence. Machine learning is a subset of AI where algorithms are used to learn from past data and predict outcome on new data or to identify trends from the past data. Deep learning is a further subset of machine learning in which algorithms are modeled to learn from complex data using neural networks. So, we have looked at AI, machine learning, and deep learning in the previous modules. And in this module, we will look at generative AI in more details. So, as the name specifies, generative AI is a type of AI that can create new content. Generative AI includes models that can create a wide range of outputs, such as text and any kind of media, whether it is images, music, videos, and other types of data. Gen AI, as you can see from the graphic here, is a subset of deep learning where the models are trained to generate output on their own. And Gen AI unlocks exciting possibilities for creative tasks, automation, and new ideas. So, how does generative AI really work? Generative AI at a very high level, the generative AI model learns the underlying patterns in a given data set and uses that knowledge to create new data that shares those patterns. To explain this in a simple way, let's imagine you're trying to teach a generative AI model how to draw a dog. You would start by giving it lots of pictures of dogs to learn from. The Gen AI model doesn't know anything about what a dog looks like, but by looking at these pictures, it starts to figure out common patterns and features like dogs have pointy ears, sharp teeth, whiskers, etc. Once the Gen AI model has trained on enough dog pictures, you can then ask it to draw a new picture of a dog. And the Gen AI model will use the patterns it has learned to generate a picture that hopefully looks like a dog. But remember, the Gen AI model is not copying any of the pictures it has seen before, but it is creating a new image based on the patterns it has learned. In practice, this process involves a lot of complex math and computation, and there are different techniques and architectures that can be used. But this is the basic idea behind generative AI. So, how does it compare to machine learning? As we have learned in the previous modules, machine learning is about identifying patterns, in this case, pictures, and using those patterns to recognize and classify new examples of cats and dogs. Like in the previous example, machine learning starts with the model being trained with the training data set. So here you see training where the model is trying to learn new capability from existing data. But now the training data set consists of a set of input features and output labels. So what we refer to as data and labels on this slide. These features could be body shape, skin texture, eye color, etc. So in this case, like in the previous example, we provide pictures of a dog or a cat, but we also provide a corresponding output label. So here there's a picture of a cat and the label says cat. There's a dog and the label says dog, and so on and so forth. During the process of training, machine learning model learns the relationship between input features and the corresponding output labels from the provided data. Once the model learns from this data, we have what we refer to as a trained model. After the model is trained, it can be used for making inference. Inference is a process of getting a prediction by giving a new data point. So in this example, we provide a picture of a cat or a dog, and the trained model predicts the output is a dog. So see here, there is no label. We just provide a picture. And then we ask, what is this? Trained model predicts that the output, it gives a label saying it's a picture of a dog. Now, this is a type of machine learning which is referred to as super. So hopefully based on a traditional machine learning model can be used for classification, it could be used for making predictions, etc. While a Gen AI model is used for generation. So it could be text generation or it could be any kind of media generation. Now, what are the types of generative AI models? There are two main types of Gen AI models. The first type is text-based, where models can generate text, they can generate code, they can generate dialogues or chat, or they can generate articles. In this case, the models are learning from large collections of text data to capture patterns, language structures, and semantic relationships. The second kind of Gen AI models are what we refer to as multimodal models. These are the models which are capable of processing and generating multiple modalities and learning from multiple modalities simultaneously. These modalities could include text, images, audio, and video. So these are the two type of generative AI models based on a very high level kind of understanding. And finally, what are the applications for generative AI? Well, there is every vertical industry and every horizontal use case is being touched by generative AI. We are already seeing its use in generating, creating content, creative content. We are already seeing Gen AI being used for image and video generation. And there's literally every use case you can think of. One use case where Gen AI is really helping a lot is medical imaging and drug discovery. Gen AI is greatly accelerating the rate of scientific progress in medicine, offering breakthrough in drug development, diagnosis, and increasing overall the rate of scientific progress. And that's pretty much it. Hopefully in this lesson, you got a good overview of what generative AI is and how generative AI differs from a traditional AI approach. I hope you found this lesson useful. Thanks for your time. Hello and welcome. In the previous lesson, we looked at generative AI. In this lesson, let us look at large language models. A language model is a probabilistic model of text that determines the probability of a given sequence of words occurring in a sentence based on the previous words. It helps to predict which word is more likely to appear next in the sentence. So what does that mean? Let us say we have this pet to the zoo to send me a pet. They sent me a blank here. This is taken from the opening of a children's book. What a language model will do is to compute a probability distribution over a vocabulary. That means that the language model knows about a set of words that should appear here. So that is what I mean by vocabulary. And the vocabulary will include words like lion, elephant, dog, cat, panther. Basically all the words which could appear in this blank here. And the language model is giving a probability to every word in its vocabulary of appearing in the blank here. So you can see there's a probability of 0.03 assigned to lion, 0.02 to elephant, 0.45 to the dog, and so on and so forth. And it is important to know that when we run a sequence of words through a language models, we are going to get a probability for every single word in its vocabulary, but no words outside of its vocabulary. So you would not see a word like a car here or a truck here or a building here because that's not relevant to the context of this particular sentence. But all these animals, because they are related to the zoo, are included, and each of them get a
चलो चलो बंद कर दो वो तो मैंने लाइव चलो लाइव लाइव से लाइव चालू कर दो मैंने की पढ़ी रहूं तो पढ़ी रहूं मैंने की भैया चालू कर लूं लाइव पे जिमोन पे काय हो कारे कारे ये धब्बा धब्बा जे काय ते माता ने करी माता ने करी